Hey everyone. In this problem, we are going to use the normal curve, which is a continuous variable, to approximate a binomial random variable, which is discrete. So let's just review how we would normally go about finding a discrete random variable. In this case, what is the probability of getting more than 510 heads in 1,000 flips of a fair coin? X is the number of heads we flip. That's what we consider a success here. So there's 510. N is 1,000. It's the number of trials. And P is the probability of success flipping a head. This is a fair coin, so that's 0.5. Now let's remember, we're trying to find the probability of getting more than 510, which is the same thing as 1 minus the probability of getting less than or equal to 510 heads. So normally what we would do is we would use our binom.dist function. Remember, the binom.dist function always finds that's the p of x is less than or equal to 510. The less than or equal to is what the binom.dist function finds. So that's why we're keeping the 510 here. That's our number of successes. The number of trials is 1,000. The probability of success is 0.5. And we want the cumulative function, so we're going to choose true here. And we get, and we have to do the 1 minus, and that gives us 0.2533. So what that means is there's a 25.33 chance that we're going to flip more than 510 heads out of 1,000 flips of a coin. So that's the way we normally do this using technology. And all the information is built into that binom.dist function. It just spits out the numbers at us. So now let's do this in a way. Historically, we didn't always have computers. What if you didn't have a computer program like Excel available to you? How would you find this answer? How would you find the probability that we're getting more than 510 heads in 1,000 flips? Well, it starts the same way. Remember, binomial random variable is discrete. We want to find the probability that we get 510, more than 510 heads, which is the same thing as doing 1 minus the probability that we get less than or equal to 510 heads. And so what we need to do a little bit differently here is, because the normal distribution is continuous and my random variable is discrete, the discrete random variable, when it calculates the probability, it does it in chunks, and we sort of leave out a little bit of area because there's no 510.5 flips of a coin when we're talking about getting heads or tails. You can't get half of a tail or half of a head. But on the normal curve, there's area there that needs to be accounted for. So what we're actually going to do is we're going to do something called a continuity shift. Okay, so this continuity shift is going to be, if we want to include the value, in this case, we do want to include 510, we want to make sure we're bigger than that value. So the probability that x is less than 510, on our normal distribution where there is no less than or equal to, it's just less than, because it is continuous, we are actually going to go all the way up to 510.5. So this is the probability we want to find, the probability of getting less than 510.5, and then we can do 1 minus that. If we were looking for the probability that we were getting less than 510, in this case we don't want to include 510, so what we would normally do is we would do the probability of x being less than or equal to 509, our continuity shift would be that we would find the probability of getting less than 509.5. So we're always going to include, we want to go above the value that we want to include, the first value that we want to include. So if 509 is the first value I want to include, not 510, then I do 509.5. But if I want to include 510, then I'm going to go up to 510.5. So now what do I do with this 510.5? Well, first we need to calculate a couple other things. I need to know what the mean and the standard deviation of my data set is. Remember, if we know what Q is, the probability of failure is the same as success with a coin. But mu is going to be n times p, the number of trials times the probability of success. And the standard deviation is going to be the square root of n times p times q. That's how I find the mean and standard deviation for a binomial random variable. And I can do that. I could do that by hand. I didn't need to use Excel to do that. So I could have found those values in a historic setting. And so what I'm going to do with these values now is find the z-score for the 510.5. So the z-score here is going to be 510.5 minus the mean divided by the standard deviation. Again, this is a calculation I could do by hand. I'm using Excel to help me do it right now. And I get 0.664. And I really only need it to 2 decimal places, in this case 0.66, because I'm going to use this table, which gives me the probability below a certain z-score. So if I have 0.66, which is right here on this table, it's the 0.7454. It's this value, because we started at 0.6 and we want 0.66, so it's 0.7454. So 0.7454 is the area below that value. So 1 minus 0.7454 gives me the normal approximation to this binomial. Notice when we did it normally, we got the normal way, the usual way, we got 0.253, and this approximation gave me 0.2546. So this continuity shift would allow us to use a normal distribution to approximate a binomial random variable, which in this case, that's pretty close. These two are pretty close to one another. So I wouldn't be mad about that. So it's saying a 25.46 chance of getting more than 510 heads instead of a 25.33 chance. But those are still really close. So that's all I have to say about using a normal approximation to the binomial curve. It's just a historic thing that's nice to know about in case you're only ever given a z-table to work off of. All right, I will see you in the next video.